Welcome back to our link layer module, and today I'm going to be talking about yet another topic that will be useful for your project and in general will be useful. So the conversation today will be about Ethernet, and additional topic on top of the Ethernet is self-learning in switches. So first of all, what is Ethernet? So Ethernet is a link layer technology that provides connectionless communication over the wire. And obviously you have to connect the wire on one side, connect the wire on the other side. That would be traditional twisted pair. But before twisted pair, we actually had the long coax cable, and you could attach to this coax cable in different points, and you actually didn't need to have switches in that universe. But let's talk about this separately. Second, the Ethernet provides unreliable transfer, so you send a packet and there is a chance this packet will not be delivered. On Ethernet we don't do any kind of acknowledgement or not acknowledgement, so this is actually different from Wi-Fi that we're going to be talking about in next part. And finally, in Ethernet we're using CSMA CD, the one that we talked before in the previous part. Okay, so now important part for the project. Ethernet frame is not that complicated. It's only have a few fields, and important fields are destination address, source address, payload, and there's a magical thing. So on the slide that you probably see, so there's 2 bytes dedicated to type or length. So this one actually interesting because it was initially in the initial specification of Ethernet defined to be length to indicate how long the payload size, and then it was actually redefined to be used for the type of the payload, like how you're supposed to interpret the payload. And kind of semi-question to you that relate to one of the previous parts in this module is, so today we're not using this field to indicate the length. But we still have to have a length, like because this is the Ethernet frame. We still have to know how much of the length in this in the payload. Like we still need to know that. So the question to you: how exactly we can discover this information? So that think a little bit about the first part in this module. Kind of apply knowledge from there to here. Additional note to the project. In the project we actually will be receiving the Ethernet frame without certain fields. So basically you're not going to get the preamble, you're not going to get CRC. So this will be handled outside our project. All addresses in Ethernet are 6 bytes. So the one that we discussed about MAC addresses previous time. And that's it. So this is extremely simple frame, and note this simplicity and remember this simplicity when we're going to be talking about Wi-Fi frames, because those are much more complicated. Why Ethernet frame is quite simple, there's actually a number of Ethernet standards that was developed over the years, and you can think of them mostly as a physical and adaptation to physical layer. So the part of on the MAC layer or like on the actual link layer didn't really change too much, but rather changed the technology how you encode the signal on the wire and what kind of wire are we using. And as you can see, there's multiple different standards that they defined. What I would like to highlight is the structure of these Ethernet standards. And as you can see, there's actually 3 parts. So there's the parts of representing number, something called base, basically the separator, and something to indicate on top of which medium it's working. So the first one is actually very simple. It's indicating basically the speed. So you can have 2, you can have 10, 100, 1,000, 10,000. So that would be basically 10,000 representing 10 gigabit per second standard. Then we're going to have a base. Base is just a name here, and then there's indication of what kind of medium we're using to transmit, and we have actually multiple options here. We're gonna have a 2, we're gonna have a TX, I guess, and something related to fiber of FX. So number 2 is simply representing the copper, and simply meaning of the 2 is 2 wires. There's like a signal wire and the shielding wire. And T is our standard twisted pair, the one that you're mostly familiar with. Fiber is a fiber optic cable. It's not really traditionally to run Ethernet on top of the fiber optics, but it's technically possible, and there is standard for that. So that's basically it for the standards. This is the number that kind of representing the IEEE standard number. So this will be for the Ethernet, and for the Wi-Fi there's some similarities of this number. Okay, that's it. Now moving a little bit further. If you just have a cable, you probably know that this cable doesn't go very far. For example, in a traditional twisted pair, you cannot actually have one segment more than 300 feet, or around 300 feet. But what if you wanted to create a network that is bigger? So you actually have multiple options. So one of the options is a physical repeater. And basically this physical repeater will get the signal on one side and simply repeat the same signal, or maybe attenuate the signal and send out on the other side. Another type of the Ethernet device is a hub, and with hub you can do similar stuff as you do with repeaters. You can increase the size of the network, or you can actually use it for the purpose of creating the network. Like, for example, if you don't want to just connect two devices but rather connect multiple devices, you can add a hub to the network and simply connect different devices to different ports. So this one almost as the one that you're mostly familiar with exceptions that these are pretty dummy devices. Like in the case of repeater, this device is simply working on a physical layer. It doesn't do anything with the kind of decoding frames or like looking at the MAC addresses. It's simply getting the physical signal, attenuating the signal, and just propagating the same signal on a different wire. Hubs a little bit smarter, but not too much. In addition to receiving the signal, they actually process in the Ethernet frame. So they decode the Ethernet frame and simply replicate the same frame on all ports except the port that they received from. It's basically almost as a repeater, but doing a little bit smarter thing. Yet another device that most of you are familiar with is Ethernet switch. So Ethernet switch in principle is very similar to hubs, but it's smarter. And what it's smarter with is actually it knows about ARP protocol that we covered in previous part. And in addition to decoding frame that is hub is doing, it's also trying to figure out to which port it's better to send the packet. If it doesn't know anything better, it will do exactly the same thing as hub. It will replicate the same information to all ports except the one that it received from. So for example, if node E is sending the packet, then this packet will be sent out to F, A, B, C. So like basically doing some form of a replication. But if switch knows, by kind of observing the exchanges on ARP protocol, then it will actually may learn that if you send in packet towards F, so then the packet will E sending to destination F, then it will only forward the packet to one specific port. So basically trying to do some form of optimization. These are three basic types of Ethernet devices. Primarily we actually today using only switches. We actually phase out use of hubs because they're not that efficient, and the use of kind of repeaters is also not that popular, maybe in some spaces. But to make it a little bit more fun, I actually presented you a few mystery boxes that try to recognize what those are. Maybe you saw them before, maybe you can figure out from the picture and answer the question in Play Pause It. I already hinted that switches do a little bit smarter thing than every other devices, and specifically what they can provide, they can actually provide you concurrent transmission and traffic isolation. These are basically the same things, it's just looking from slightly different perspectives. So for in case of the concurrent transmission, if you send in a packet, like if two groups of stations are sending packets to each other, so in this case A to B and C to D, then if a switch is smart enough and have enough information, then these flows can go full speed. So they completely don't interact with each other, they don't need any kind of CSMA CD, they will not ever interfere with each other, so they can send at the full speed. I mean, this still requires a capacity of the switch fabric to support this, but in principle they can do that. And in addition, as I highlighted, isolation is exactly the same thing. Like if you send in from A to B, C to D, then the packets like from A will not be absorbed by D, or packets by B will not be absorbed by C. So this is interesting security principle. It is still not a guarantee, but it's actually a very interesting property of switches. And the cool part of switches is actually they don't require any kind of configuration. So remember, in the routing tables, we have to run the routing protocols. We have to do this, we have to do that. In switches, you don't do anything. You just power them on, and that's it. They will eventually learn how to do stuff. Let me talk a little bit about the mechanics of the switch. So essentially, in order to provide you with efficient transfer, you have to have some kind of a table equivalent to routing table. But in the case of switches, it's actually a switch table. It is much simpler, but it is some form of a table that exists. And how entries are created there, obviously already highlighted that the entries added there automatically. Switch received the frame. For example, this frame is destined to node A, and it looks up MAC address as part of the switch table, and there's literally individual MAC addresses listed. There's no any kind of a grouping, there's no subnets of any kind. There's literally, if there's a MAC address present, then it will indicate which port it should be this packet sent out, or ports to this packet to be sent out. So it will figure out that it needs to be sent out on port 1, and it will be sent out on port 1. That's it, end of the story. There's one small addition to, in this case, each entry in a switch table is associated with some form of a TTL, meaning that the entries in the switch tables are temporary and will be erased and will be relearned. The process of learning is actually quite simple. What switch is doing is simply observing the traffic. So it received the frame, and as soon as it received the frame, it knows the source address of the sender. And it literally associates the source address of the sender with the port that a future transmission will go to that destination, if somebody will reply to that destination. If you ask me how you actually learn stuff, like, because you got the packet, you have no idea where to forward, and yet you want to learn eventually where this destination is. And it's actually very simple. What we do, we simply, if we don't know how to forward frame, like if we simply don't have an entry in a switching table, we do the same as we do with the hubs. We simply forward packets to all destination in this environment. To illustrate what I was just saying, simply assume node A is want to send a frame towards A prime. And what it's gonna do, it simply will create this frame and send it out to the network. And just as a small note, initially we don't have anything in the switch table. As soon as switch receives this frame, it knows that this frame came from A, because it's literally observing the address, kind of source address of from the frame, and it knows that this frame came from port 1. That's it. Now it knows exactly that for the future reference, if someone will send the frame towards A, it will need to be sent out to port 1. That's it. But again, it doesn't know what to forward for the A prime, because there is no entry for the A prime. And the operation is quite simple. It will forward this frame to every single port that's available in this network. It will forward 6 to 5 to 4 to 3 and obviously to 2. And that's it. So this will be end of the operation. However, as soon as one of the nodes, like in this case A prime, will actually receive this frame, and it will potentially create some form of a response. So now what we're gonna have, node A prime will create a new frame with the source A prime with destination A, and it will again present this frame to the switch. As soon as switch receives this frame, it again doing exactly the same operation as before. It will record that A prime is now connected to port 4. So with the A prime, port 4, and set some whatever TTL this switch is configured to. Now with the next step. So we're done with the learning part. Now we're going to forwarding. In this case, there's actually already an entry for A. So now the switch actually knows that to forward the packet to A, it needs to forward to port 1. And it will forward to port 1. And the conversation will be ended. So effectively what we saw, like in initial stage, when we don't know how to forward, we basically broadcast. As soon as we know how to forward, we do unicast. That's it. That's very, very simple, very kind of smart approach, but it provides very easy way to learn where to forward packets simply by observing traffic flow. Moreover, so the conversation that I just had was based on a single switch. But it doesn't actually matter how many switches in this network, because it's simply each switch will learn slightly different thing. If, for example, node A is trying to send some packets to node I, let's say it's going somewhere else. So this node A will create a frame. And this frame will effectively indicate that it's a source from A, that is destination to I, and it will include some kind of a payload. And this frame will be presented to multiple switches. So what's going to happen initially, so when we have no switch table, like no information in those switch tables, switch S1 will learn where A is. And A, let's say in port 1 from the perspective of switch. Then switch 1 will have nothing else to do except to forward this packet towards B, towards C, and towards the other switch. So that's what will happen. Node B wouldn't respond, node C wouldn't respond, and switch S4, basically what we try to do is try to do exactly the same. It's using common frame. It learns that the A is on port, again, 1, 2, 3, on port 1. It recorded like in its internal switching table, and it's do exactly the same operation again. It forward packet here, kind of to port 3 and port 2. Done. Now this packet effectively been received by S3 and S2, and all of them will do exactly the same. Like they will record that the A is now from this side, the A from this side, and broadcast this packet to all available ports. And what eventually will happen, so node I will respond with its own frame, and now S3 will be able to effectively forward this packet directly to S4, because it already have the switching table, and it learns now that I is connected to this port, kind of directly connected to the port. S4 will do the proper forwarding. It will record that I came from port 3, and it knows how to forward towards A, to port number 1 directly without doing anything else. And S1 will be effectively forward back to A, and the conversation will be done at this point. So as I said, it's a very simple mechanism, but yet it gives the ability to learn where nodes are. Obviously, there's always some form of a secret sauce in all kind of self-learning, and the secret sauce in switch self-learning is the concept of a broadcast domain. It's nothing too special, but rather just think of it's a network segment which will receive the packet if not a single switch knows how to forward this packet directly. So basically, if all switch table on the previous picture are empty, then the whole network that is shown here is one broadcast domain, because you send a packet and this packet effectively will replicate it and deliver it to B, C, D, E, F, switch 2, switch 4, switch 3, G, H, I. So all of the nodes will effectively receive the packet, and that's why kind of the domain of broadcast. The reason I'm highlighting the broadcast domain is just to highlight that the Ethernet segments or the Ethernet networks not supposed to be too big for the scalability purposes. Because if your network spans like thousands, kind of hundreds of thousands nodes, then a single packet, like a single packet that being sent out through this network may result in this packet being forwarded to everybody, which is not necessarily a good approach, especially if you want to send some kind of secret packet or you're trying to optimize the data delivery. So in IP networks, this actually doesn't happen. So IP network is not considered to be broadcast domain, because as soon as you send the packet to specific IP destination, then its router will decide where to forward, whether interface 1, 2, or 3, forward this packet, and so on. In broadcast, if a switch doesn't know what to forward, it broadcasts everywhere. If the other switch doesn't know how to forward, it broadcasts everywhere, and will potentially result in a really bad traffic distribution. So basically some form of in-network duplication, as we saw in IP multicast, but this in IP multicast that is intentional. In a switch network, it's less intentional, but rather it's a property of the communication network. And another problem in Ethernet is not necessarily related to broadcast domain, but related to the fact that the packet, the Ethernet frame that we just observed, doesn't have any mechanism to kill itself. As you already saw in the IP frame, remember there is this TTL field. So, and every time the packet being forwarded, the IP router decreases this TTL, and if happens that the TTL goes to 0, then this packet being killed and some form of error message returned to the sender. This does not happen in Ethernet. In Ethernet, as I highlighted, we only have destination address, source address, some type of or length, payload, and kind of some other information. So it's a preamble and CRCs. So there is no TTL of any kind. There is also no notion of remembering the packet. So like that was happening in OSPF. So remember, in OSPF, you receive the packet, you remember that you received this sequence number, and if you receive this packet again, you remember it, you kind of recognize that you saw it again, and just stop forwarding. Again, this also does not exist. So this is actually critical and very dangerous problem in Ethernet. So in this very simple example, if S1 send in a frame and S2 send in a frame again to S3, and somehow S3 is connected to S1 and it's kind of sending this frame back to S1, S1 has no idea that it was actually originated this frame. And it will have to forward this frame again. S2 will forward, S3 will forward, and again S1 received the frame, and we created a new loop. And this will happen forever. So this will build this kind of frame will be looping and looping and looping until you actually power off one of these devices or disconnect one of the links. So this is a huge problem, and basically it's indicated by the broadcast storm. This was a huge problem in when you use hubs, because hubs are very simple devices, because you can create some form of a broadcast storm with the hubs. Luckily, switches do a little bit smarter thing. So switches actually trying to detect that you created some form of a loop, or you have two switches, you kind of accidentally connected two wires together or created a loop in some other way. So in order to avoid that, they're actually running spanning tree protocols. This is very similar to what we already learned in IP multicast, but it's just done on a much lower layer. So it's basically whenever you connect a wire to the switch, they will do some form of exchanges, figure out where you are, where you're connected, will detect whether you're on a part of the kind of spanning tree, not on kind of disconnected link, as on kind of inside the spanning tree, and either enable this link or disable this link. So kind of with today's switches, it's not that a big problem. Like the broadcast storm is not that a big problem, but it's still a problem because you have to detect, kind of run some form of a spanning tree in order to disable looped links and to avoid any potential looping in the system. Okay, so this was a little bit intensive part. I wasn't expecting it with that long again. But in any case, so this time I have talked about Ethernet. We covered a few standards of the Ethernet, to cover the properties of kind of that it's unreliable, there's no kind of an X, it's running on top of CSMA CD. We covered frame, and remember that we have a destination address, we have source address, we have, which are both of MAC addresses, we have type length, technically it's used as part of the type, so type of the payload. And we have some form of boundaries and error checking as part of the frame, but not necessarily when we capture the frame. And beyond that, I showed you a few devices. We talked about repeaters, we talked about hubs, we talked extensively about switches, and especially what we talked, and this is part that you need to remember for homeworks and for the exams, is switching table. If the examples that I show you kind of during the lecture is not enough, please look around. There's a tons of other examples that you can do, and some exercises about the switching tables. But remember, in switch tables is quite simple. You receive the packet, you learn from the received packet where this packet from. Basically using the MAC address, source MAC address, and using the port that you received from, and this creates the entry, and that's it. And if you know how to forward the packet directly using the additional lookup in the switch table, you will do that. If you don't, then you simply replicate the same packet over all available ports on a switch. Okay, so now done with this part, and see you next time.